When designing beams, there are two main effects that need to be considered. The first of these is known as shearing, and this is the effect where two adjacent parts of a beam are forced to slide relative to one another by the applied forces. In everyday life, a most common example of shearing is using a pair of scissors to cut a piece of paper. In engineering, bolts quite often fail due to the shear forces applied to them. The second effect is known as bending. This is perhaps more common in everyday life, and it's when the beam gets forced to curve due to the moments and forces that are applied to it. So when designing beams, we need to consider these two effects and check that the beam has sufficient strength to resist them, and also that the effects of bending and perhaps shear don't cause excessive deflections. So to understand how beams resist both bending and shear effects, the normal approach is to imagine cutting a beam. So in this example, we've got a simple cantilever with a point load on the end, maybe a diver in a swimming pool on a diving board. So if we imagine cutting the beam some distance from the end and thinking about what would happen to the piece we've cut off, then two things might happen. One is it would drop vertically, and this is the effect of the shearing on the beam. And the second is that it might rotate about the cut, and this is an example of bending in the beam. We know in reality that this doesn't happen if we don't cut the beam, but there must be forces preventing both the vertical movement and the rotation, and it's these forces which are internal to the beam that are known as the shear force and the bending moment in the beam. Shear forces are normally given the symbol V and indicated by an arrow with just one head, and bending moments are typically given the symbol M. Now, because these are internal stress resultants, like an axial force in the beam, we have what's called deformation sign convention. So with an axial force, we say tension is positive. With shear force, we say if the shear force is tending to rotate the small chunk of beam that we've imagined cutting off in the clockwise direction, then it's positive. And we say a bending moment which tends to curl the beam so that it's sagging, as in the diagram there, we say that that is positive. These are the normal sign conventions for analysing beams. So with those ideas in place, we can then ask, well, how does the shear force and the bending moment vary along the length of a beam? And so sticking with the example of a cantilever with a point load, we're now going to imagine taking a cut not at a specific position, but at some distance x from the end of a beam, where x can vary. If we do that, then we can consider the equilibrium of a piece we've imagined cutting off, and the first thing we see is that the shear force has got to equal P, the load acting down in this example, and that this is completely independent of the value of x. If we took our cut near the tip of the beam or near the support, the shear force would still be P. The bending moment is a little more complicated. This does vary as we move along the length of the beam. If you imagine taking a cut near the support, then x will be bigger, and the bending moment will consequently be bigger because it's given by the force times distance, which is P times x in this case. There's a negative sign in there, and the reason there's a negative sign in there is because of the sign convention we defined a moment ago. The force on this beam is causing the beam to deflect so that it's hogging being the opposite of sagging. And so we've now got relationships for both the shear force and the bending moment, and we can plot these along the length of a beam, and this is known as a shear force diagram and a bending moment diagram, and we can see that the shear force, as our equation is telling us, is constant in this case, whereas the bending moment increases linearly from 0, just under the load, to minus PL, where L is the length of the beam at the support. And so in this case, the beam would need to be checked for strength at the support, because it's at this point that the bending moment is at its maximum. So these are the key concepts for shear forces and bending moments. In more complicated problems, the algebra gets a bit more messy, but the ideas remain the same, and the idea of plotting a shear force diagram and a bending moment diagram is key to understanding many structures.